in the previous class, what we have seen the swing equation. Okay, remember we have seen the swing equation. That swing equation is this one. Okay, here m was the, are you seeing the screen now?
Yes, ma'am.
Okay. M was
Yes, ma'am.
the angular momentum, and this one was the angular acceleration, and pa was accelerating power, ps was mechanical input power, p was electrical output power. Okay, now today actually why that swing equation is used to find the stability of the system. So from this equation, swing curve is plotted, and from the swing curve, if you remember, from the swing curve we can find out whether the system is stable or not. Okay, now let's come to today's topic, which is just wait a minute. Okay, let me change the equal area. Okay, today's topic is this one. Okay, equal area criteria. Are you getting?
Yes, ma'am.
Okay. So now this from the swing curve also we used to find out the stability of the system, whether the system is stable or not, by plotting the swing curve. And this equal area criteria is also used for find out the stability of the system. Okay, equal area criteria. So what is that? Now why we are not going for a swing equation? That is the question. Like, swing equation actually involves numerical techniques. Okay, numerical techniques, and it's the time consuming process. That's why numerical technique, if you remember from the maths, it's a time consuming process. That's why we will not use swing equation, or we do not use swing equation for finding out the stability of the system. Now that's why equal area criteria is used. And equal area criteria, what is that? It is the graphical method of finding out the stability of the system. Okay, graphical method of finding out the stability of the system. So what is that now? And why do you need to find out the stability of the system? If you see, yeah, in the day before yesterday's class, I have mentioned about the oscillation of the rotor angle or load angle, dynamics of the system. So that is the thing where delta oscillates when delta. Now what was delta? Delta was power angle in case of transmission line, and delta was rotor angle in case of synchronous machine. So here we will go for the synchronous machine characteristic. So when this delta oscillates around the equilibrium point with constant amplitude, okay, means what? There is a okay, let me show you something here. This. So suppose the variation of delta is in this region. Okay, are you, this screen is visible?
Yes, ma'am.
Okay, from this point to this point. Okay, this is suppose the limit. This is delta is equals to suppose 0 degree to 90 degree. So if delta oscillates between these two, okay, then transient stability can be maintained. So that is the thing actually. That is the thing when delta oscillates around the equilibrium point. means if due to the heavy load change or due to the fault, transient stability arises. Okay, transient stability arises. For that one, delta changes. Okay, delta, what was delta for the synchronous machine? That was the difference in angle between the stator magnetic field and the rotor axis. If you remember the swing equation, first one diagram was there, no? Theta, delta. Remember? Do you remember? Answer me. Do you remember that?
No, ma'am. Oh,
You have remembered, no? Or should I show?
yes, ma'am.
The screen, then I have to come back. Okay, I think that this type of diagram you remember. Let me draw. This type of diagram was there, remember? Hmm? This one was omega s speed. This one was rotor axis. Remember?
Yes, ma'am.
Rotor axis, huh? I'm not able to write it properly. And this one was reference axis. Okay, reference. And this angle was delta. Huh? This angle changes. Why? Because this will rotate at synchronous speed only, but this will change. And when load changes, this line will change because of the rotor speed changes, and delta will change based on that. Now, if you see this one, okay, when that delta changes from 0 to 90 degree, for example, then equilibrium can be maintained. And the transient stability will also be maintained. So we'll take the swing equation to find out the equilibrium criteria. One of you please take the screenshot of this one, whatever
Wait,
is
ma'am.
okay. One of you please take the screenshot, then later on you can send me. So we will start from the swing equation. Okay, this one was our swing equation. Here, this PS is the mechanical input power to the generator or alternator, and electrical output power. Now PA was accelerating power. Already we know this. Now we'll start it from here. Now what we will do here? Multiply this equation. Multiply. You do one thing. Hello. Hello. Okay.
Can you show
Multiply this.
that first one?
Sorry.
First one. I will take the screenshot.
A screenshot, actually, that the classes are going on, not that screenshot. Huh? You go to that some photos or something will be there, na, names and something.
Okay.
Now I think you are getting the screen, but go back to your this how many people are joined there. Okay, I will do then, no problem. Okay, let me explain first. So this is the swing equation. Now, hello. Now we multiply this equation both side with d delta dt. Now see, here d delta dt will come, again here d delta dt will come. Okay, so this things is this one is done here. This into d delta dt, ps into d delta dt, p into d delta dt. Okay, then d delta dt is taken common, and ps minus p. Okay, now here if you see this equation actually modified as in this way: derivative of d delta dt. Now, if I take the derivative of d delta dt square, what will be the derivative? Suppose the dt of t square, then 2 will come here. Can you find this here? 2 will come, na?
2.
What will be the derivative of d delta dt? Let me show you there. Just derivative of d dt of d delta d t square. Okay, So what will be the derivative of this? This will come, 2 will come, no? 2, then what will be there? D delta. To d delta dt. Yes?
DT.
Yes, ma'am.
Okay. Now you come to this screen again. See. So 2 will come here. Then 2 will get cancelled. Is it?
Hmm.
2 will get cancelled. And another thing, if you go to that screen, whiteboard, into,
Ma'am, which two will get cancel? Will get cancel.
wait. D square delta d t square. Okay. Now see this equation. What we have? We have this much now. 2 d delta dt into d square delta dt square. Okay. If we take the derivative of this part, now we'll take this one there in the equation. See this one here. In place of this much, d delta derivative of this one, I will put the whole equation. 2 into what it was? D delta dt into d square. What it was? Two into d delta dt into d square delta dt square. Why does it come? Because again we have to take the derivative, no? Because this is not directly x. Some other terms are there. That's why. Now, if we put this one in this equation, what we will get? We'll get this half is there now. Why half is multiplied? Because 1 2 will come here. So 2 will get cancelled. Only d delta dt square and this will remain. So from this equation you can get this equation. Okay, if you take the derivative. See here, derivative of this, what we have, you have seen, no? Oh, tell me something. Give me some response. Derivative of this I already told you, no? There, have you understood this part, derivative?
Yes, ma'am.
Okay, so if I put this one in place of this much, okay, I will get this equation. Okay, so that is equals to this one. Okay, ps minus p into d delta dt. Now next what you have to do, you multiply it by multiply this equation, the above equation, with dt and take integration. So if you take integration and multiply it, this equation with dt, we'll get this equation. Okay, now integration limit is taken from 0 to delta, delta 0 to delta. What is delta 0? Delta 0 is the initial operating angle and delta is the final operating angle. Okay, so if you take the integration and see 2 was there, na? 2 is there, so 2 will come up, m will come down. Okay, in the numerator 2 will go, denominator m will come. So if you see the equation, see 2 is in the numerator, m is in the denominator. Okay, and multiply both sides with dt. So this you will get this much. Now what will be d delta dt? D delta is root of this equation. Okay, now next come where delta 0 is the torque angle at which machine is operating. Okay, while running at synchronous speed, means at the normal condition. That's why I told you initial operating angle is the delta, where machine runs at synchronous speed. Okay, there is no disturbance, and there is no disturbance means before disturbance d delta dt is 0. See, if there is no disturbance means the angle, let me come to this one. If there is no disturbance, this angle will be fixed. Okay, because rotor speed is not changing. That's why this angle is fixed. If this angle is fixed, what will be derivative of angle with respect